Okay, so last class we talked about representations and how we can compose representations, and there's a simple way to represent everything is just binary strings, right? And there are various forms of representations, and some are more efficient than the others, but for us efficiency was not a big concern because we are trying to model like whether you can compute or not even, right? Not how well you can compute, at least for the time being. So for going forward, we said that in everything, all inputs are just binary strings. And this is without loss of generality. It's not as if you're building a toy model where you can only do string operations. You can manipulate graphs, images, everything, just because it's all binary strings. And today, we're going to take this assumption that everything is just binary strings and start talking about building our first model for computation. It is going to be limited in some way, but at the same time, it's also very powerful and historically was very important in developing modern computers. And that's the notion of Boolean circuits. And then I'll briefly talk about various physical devices which are kind of can do this circuit computation in the real world. If you're interested, this is chapter 3 of text. Also, one important announcement, homework 1 will be out today. This will cover the first 4 lectures, and it will be due next Monday at 10 p.m. And the homework will be released on the class website. Just click under the homeworks there. And you should all be able to register on Gradescope by an email that you'll get and upload it there. Okay? Any questions about logistics? Okay. All right, so let's get started with the actual class. Okay, so first, a bit of history. What are algorithms? Does anyone know where the word algorithms comes from? Any guesses? No, yes. Well, I mean, I wouldn't have guessed it myself, but basically there was this 9th century mathematician by the name Al-Khwarizmi. And what did this mathematician do? He gave an algorithm, or gave a procedure, let me call it. Let me not jump ahead, to solve quadratic equations. I mean, nowadays we do this in elementary school, right? Or in kindergarten, but at least in 9th century, it required a major mathematician to actually find a procedure, just a mechanical procedure to solve any quadratic equation. I tell you x squared minus 4x plus 10 equals 0. How do I solve that? You follow this recipe for it. And that's what he did. And it kind of, maybe the word starts with this word. So part of the origin is his word. But informally, can anyone define what an algorithm is? I mean, what is our goal, right? Our goal is to build a rigorous mathematical model of what algorithms are and what they can be in the near future. But informally, what do we think of when we say, okay, here's an algorithm to solve some problem? Any guesses? Yeah? Okay. A series of steps, to solve the problem. Whatever the problem is, like, I want to solve quadratic equations. And here's a series of steps. I want to bake a cookie. Here's a series of steps, right? So these are all just algorithms. Any cooking recipe is really just an algorithm. Okay. This is informal for 2 important reasons. One, it's easy to define series, right? You're doing one after the other. But how do you define a step? Right? So it's informal because the notion of steps is not very clear. What do you mean by step? What might be a simple step for me might not be a simple step for someone else. Right? What might be a simple step now might not be a simple step 10 years down the line. Like take the example of quadratic equations. You might take it for granted right now, right? Okay, solve this quadratic equation, do something else on top, and then you do something else, right? So that's something that we have to address. And then we should also look at what we mean by solve the problem. How do I mathematically state the problem? Now, what is the mathematical thing I'm trying to do when I say, okay, find me a shortest path in the graph, find me a cycle in the graph, check if this image has a dog or not, or a dog or a cat. Okay, so we have to define or find a way to talk about these two things. How to formalize this. Of these two, formalizing the second one, solve the problem, is easier than the former of formalizing steps. Okay. So let's start with how we are going to define solving the problem. Right. So when we say solve the problem, what we really mean is that we have some notion of inputs that we have in mind, and then there's a desired output, right? So we want something which transforms inputs to desired outputs. Okay. Mathematically, this is just a function, some function, whatever it is, from the space of inputs to the space of outputs. Okay. So, from now on, when we think of specifying the problem, we should just think of, okay, there is some desired mapping I want. Given inputs, I want you to tell me what the output is. I give you two numbers, the output should be the product, right? So that's my desired mapping. Okay. So that's the specification of the problem. So for us, we'll say, as we said, all inputs are just binary strings. So, and all outputs can also be assumed to be binary strings, right? Because no matter what your real thing is, we can eventually just encode it as binary strings. So specifying a computational problem for us is just specifying a function from inputs, which is binary strings, to outputs, which are also binary strings. Okay, that's it. So let me box that. Specification is function f from this space to this space. Okay. And often, sometimes you might think of there just being a single bit output, many times there are multiple outputs, whatever it is, right? It's not that important. And I mean, the language here might be a bit confusing because in programming, when we think of a function, it's something, you just, let's say print is a function, right? But that's not really a specification, it's an implementation. And there's a difference between how you specify something and how you implement. For instance, if I write down the function, which is, let's say, multiply, which takes two integers, two natural numbers, and outputs a natural number. Okay, this is a specification. And there may be many different implementations or algorithms which carry out this specific goal for us. Okay. Any questions about this? Yeah. That's a good question. So again, what we're trying to understand is when you're doing the side effects and so on, there's an underlying goal you're trying to achieve, right? And that goal is what we're targeting. Like, maybe your goal was to transform the memory into something else, right? So then the side effects are important because they are changing the memory state, right? If my goal is to actually run the program, then keeping track of the side effects is important. But if my goal is to just multiply these numbers, then I don't have to care about what happened to all the memory that I didn't use or use but didn't garbage collect or anything like that. Okay, so it's, I mean, basically just think of what is the function that we're trying to compute, and then think of the various ways of implementing. It's a good question. Any other questions? Okay, so as I said, the notion of solving the problem is not that complicated. And one way to picture this is via truth tables. It's a really boring way, but at least for small examples, it's illustrative. A function f is essentially, as I said, a mapping from inputs to outputs, right? So you can imagine I write down all possible inputs on the left of this sort of huge thing. And for each input, I write down the corresponding output that I want. Okay. So this is sometimes called the truth table. I mean, this is not generally useful, but for some examples that will come up, it's good to keep in mind. All right. So this is good so far. We have specified what it means to solve the problem. But how about steps? Any guesses about that? How do I define steps? Right. So the intuitive notion that we had when we said algorithm is it's a series of steps. But what should steps be? Can it be like, can I put in any Python library there? Or maybe I can go one level up or one level down. What should I do? Yeah. Right. So, well, we already did the series of steps. We now are at a stage where we want the notion of step to somehow be atomic. And we don't want it to be further indivisible because we already did that. Okay. So these are some basic operations. Okay. In some sense, if you think of an algorithm as a wall, these should be like the bricks, right? So you want your steps to be the minimal sort of unit that is going into your computation. And you can come up with all kinds of things for what steps might be. And all of those would make sense. For instance, for modern processors, they have inbuilt steps for just multiplying, right? And if you take GPUs and ML processors, they have inbuilt steps, which are basically hard-coded hardware chips, which are very good at doing matrix multiplication. So you might think, okay, let me take that as a step in my computational model, right? We can do all of those things, but here we want to build something which does not change with technology, right? We want a model that is good enough to capture what is possible to be computed, not just now, but 100 years down the line, right? Any questions about this? Okay. So one of the most fundamental models here is what are called Boolean circuits. going to be a very simple model and as simple as it can get. And as we'll see, it's actually very powerful. It can capture pretty much any other notion of computing that you can think of. Okay. And what are Boolean circuits? These are, in a single sentence, computing with and, or, / not as basic operations. Okay. So we're going to view Boolean circuit is essentially an algorithm where you have a series of steps, but the steps are extremely basic. They're only going to be and, or not operations. That's it, nothing else. Okay. So what are these operations? I'm sure every one of you here has already seen them, but let me just write them down for concreteness. So these are logical operations. So we have and. I'm going to view and as a function. I'm going to specify what it should do. It takes 2 bits as input and outputs a bit. And of a comma b of 2 bits is 1 if both are 1 and 0 else. Okay. Similarly, or also takes 2 bits as input and outputs 1 if, okay, let me write it differently, is 0 if both are 0 and 1 else. Okay. So and is just saying, okay, both the bits have to be 1, only then I'll output 1, or is at least one of them needs to be 1, and when that happens, the output is 1. Okay. These are functions which are only taking 2 bits as input. And finally, what is not? Is a function which takes a single bit and outputs a single bit. Not of a is 1 minus a. Not of 0 will be 1, not of 1 is 0. Okay. Any questions? I'm sure you already seen this before. Sometimes and is actually written as this wedge or inverted V. This is math or logic notation. Or is written as a V. And not, we'll just use not for it, is short enough. And sometimes you can use symbols like this inverted L or a twiddle, different ways of denoting the same thing. Okay. All right. But let's also do one thing, which is look at the truth table. Okay. So what does the truth table of and look like? What does the truth table of or look like? Okay. So these are the inputs, these are the outputs, right? So and on input 0, 0, the output would be 0, 0, 1, the output is 0, 1, 0, 0, 1, 1 is 1. Okay. And or 0, 0 is 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. And finally, 0 becomes 1, 1 becomes 0. All right. So we are going to build computers, or basically we're going to build a model for what algorithms can do just in terms of these three basic operations. Okay. So before before doing that, let's do some simple properties. Again, I'm sure you've probably seen this before, but I want to go over them. What are some properties of AND and OR that you know of? Can you tell me? Maybe one or two? You can think of them as some operations, right? In some sense, they are like the addition and multiplication, but in the binary bits world. Okay. So what kind of properties do they satisfy? Any guesses? Yeah. Commutative, yep. Right. So these are both commutative, meaning the order in which you enter the bits doesn't matter. Okay. What else? There is associative, right? So A and B or C and C. So if I'm doing three operations, it doesn't matter which I do first, right? I can do A and B and C, or A and B and C. And the same for the OR operation. Okay. This might seem very obvious, but these properties are actually very important in the way we are going to use them. This allows us to not worry about the order in which we perform multiple ANDs and things like that, and simplifies notation a lot. Okay. So from now on, if I am doing AND of three things, I can just write A and B and C, because there's no need for any ambiguity there. Any other properties you can think of? Yeah. Yes. There's also distributive, meaning A and B or C. Again, this is like, as I said, multiplication and addition. Right? So if I'm doing A and B or C, then I can push the OR inside. Okay. All right. So, these are our basic operations. Let's now do a toy example of an algorithm for a simple task. And what's my simple task? The problem I'm trying to solve is compute the majority function on 3 bits. Right, so let me say majority 3, which takes 3 bits as input and outputs 1 bit. Right, so the majority is 1 if and only if at least 2 of the bits are 1, right? So you have 3 bits. Whenever at least 2 are 1, you have to output 1. Otherwise, you have to output 0. Okay. How can I compute majority if what's an algorithm for computing majority if my basic steps are only and, or, and not? How can I do that? Any suggestions? Yeah. Right. Yes, that's an excellent idea. We'll do that. But here, since we know majority, we can shortcut that a little bit. Okay. So in particular, we have to output 1 when there are at least 2 ones. Right. So we can say something like the output should be 1 when A and B are 1. Okay. Or B and C are 1. Or C and A are 1. Right. So this is checking that at least 2 of the bits are 1. And this is evaluates to 1 only when at least 2 of the bits are 1. Okay, does it make sense? What was suggested would also work, but it would just take a little longer to write down. Okay. So if I were to write it in a notation, I'd say OR of AND of A comma B, comma AND of B comma C. Yes. If I were to write it in the functional notation, then I would say okay. This is what the entire thing would be if I were to write it as functions, right? We said the simple steps are AND OR, and that's enough to write this. Evaluate the majority on 3 functions, 3 bits, sorry. Okay, let's do one more example, or actually we'll do a couple more, but the next one is XOR. All right, so it's a function again which takes 2 bits and outputs 1, and I'll just write down the truth table. I think that's easier for this guy. So if I put 0, 0, the output is 0, 0, 1, 1, 1, 0, 1, 1, 1 is 0. So basically XOR is 1 when there is exactly 1 in the input. If there are no ones or there are 2 ones, then it's 0. Okay. How can I compute XOR using AND and ORs? Actually, that's a wrong question because you cannot compute XOR using just AND and ORs. You also have to use the NOT gate now. Yeah. Right. So that's an excellent suggestion. So let me write that down. Not A comma B. Oops, sorry. A and not B, right? That's what you said. Comma not of B. And then OR of the same thing flipped. Okay. So if you were to write it in logic notation, this would be A and not B, or not A and B. Okay. So you're basically looking when the function evaluated to 1. So either one of them had to be 1 and the other 0, or the opposite. Okay. Any questions about this? Okay. Finally, let's do one more, which will illustrate something that we always do when we write code. Okay. So let's say now I ask you to compute XOR on 3 bits. So what is the XOR function? I'm not going to draw the truth table. It will have 8 entries. Is 1 if and only if an odd number of bits are 1. Okay. So either there is exactly 1 1 among ABC, or all 3 are 1. That's when you're going to output 1. Otherwise, you're going to output 0. So how can I compute XOR as using my basic steps? Any guesses? Any suggestions? Well, think of what you would do if you're writing program, right? You wrote down something for XOR 2, and now I'm asking to compute XOR 3. What's the natural thing to do then? To reuse the code, right? That's the best way to write programs, which is, you want to reuse the code that you already written. And how can I reuse that code? Well, XOR of 3 bits is just, I can XOR A and B and then XOR the output with C. Right? Okay. So what I'm doing here is I know how to compute XOR on 2 bits. I'm going to do that on A and B, and then take that output and compute its XOR with C. So if I wanted to, I can go back to my and or not expression for XOR 2 on 2 bits and redo the whole thing, right? And I'll just get a series of simple steps, which are and or not operations, which will tell me the answer of XOR. Okay. Any questions about this? All right. So let's see what we did so far, right? We defined what it means to solve the problem. Okay. Solve the problem meant compute the function. Okay. So you have some corresponding function which specifies what you're trying to do, the transformation from inputs to outputs, and we wanted to match that function. And basic steps. For whatever reasons, which are not at all clear so far, I said, let's choose and or / not. Okay. This is very ad hoc, right? There are many things which seem even more basic, right? Maybe I should just start with addition and multiplication. Why not that? Maybe division, right? I can do all kinds of things, but I'm only choosing and or not for now. Okay. And what this will allow us to do is to define the notion of Boolean circuits. You can use these to define an important model of computation called Boolean circuits. Okay. And before going on, let me actually say something about where these come from. As you'll see in a little bit, Boolean circuits are really made up of and or not gates, right? And I'm saying, okay, it's a good model for computation. And one of the reasons it's a good model is that we have, and in fact, this was the way that some of the modern computers were first built was by giving physical implementations of Boolean operations. Okay. So what do I mean by this? I mean, everything we're doing so far is just very mathematical, right? I'm saying, okay, you can define and or not this way. And here's one way to define a sequence of operations which are going to define circuits for us, right? But at some point, we want to do something with it, right? I want a device which does this computation for me, right? Not just me mechanically doing it. I'm not gaining anything. I want some device, a computer to do it, okay? Fortunately, people developed various technologies over the years to do the basic operations first, and or not. How can I do that just on a device, physical device? And then once I can do that, I need to figure out how to chain them, how to make a series of those steps. People developed many technologies for this over the years. The first one was vacuum tubes, and then transistors. You can, there were transistors specifically for doing and or not operations. And then you could chain them and get to perform any series of operations. People have used DNA sequences on cells to implement and or not gates. And you can even build computers with that using the Boolean circuit model that we're going to talk about. You can use chemical reactions. You can use fluids. One of the most ridiculous but fun things to see that you can use pipes and water flow to build a computer. And the core of that is, again, I can do and or not using that. You can use marbles. All of these to implement and or / not. Okay. So let me show you a quick video of one of those things. Okay. So here's and. Only when water is flowing through both will water go through. This is or, meaning water is flowing through any one, you'll get. XOR, water is flowing through both, it doesn't go through. No water, obviously there's nothing. Okay. And there's this whole area of fluidics, which tries to build bigger processors or what have you using these basic operations, right? So whenever you can do these basic operations, you find a way to implement them. You can use the model of Boolean circuits to build on top of that. And if you go to MIT's data center, they have this huge DigiComp 2, which apparently was a game that came out in the 80s. Which again is something similar. where you can change the positions of these things to implement Boolean circuits. Okay. Basically, each one, the way it goes will dictate whether it's an AND or an OR gate. And then you can chain them using the various modes. And that gives you an implementation of Boolean circuit, a physical device which can implement a Boolean circuit. Okay. And people have really dug into what's the power of Digicom2, what can it compute, what can it not compute. There are papers written on it. It's a fun topic. Okay. So what we'll do now is take these basic operations and see where or how far we can push it. Okay. So let's do one last thing, which is, you can see, well, I already drew the two tables. Maybe this is not important, but yeah. Okay. All right. So let's take a 5-minute break. And when we come back, we'll define the model of Boolean circuits using the simple operations, which we now know that can actually be carried out on physical devices. Okay. All right. Yeah.
Earlier in the notes, you wrote MAG3. I was wondering what that stands for.
Majority.
Oh, majority.
Majority on 3 bits.
Of the 3 bits, right?
Yep. Yeah.
So you said that an algorithm is mapping from a string to another string. So why wouldn't the basic operations be like appending bits or removing bits and splitting them?
You could do that too, but I think you want the operation to be really, really basic. Like, if I say it's an operation on 100-bit strings, maybe that's not basic enough. You want to further break it down, right? You can think of AND as something like that, but it's a bit more conditional, right? If it's 0, 0, you can see a stripping, maybe. I'm not sure. And you could probably build a model out of what you said. Let's say the only operations I allow are take a string and they can specify, you can cut something and put something together. And as something that will come up is, given any such sequence of basic operations, you can check its power, right? And whether it's a good set of basic operations or not. In some sense, if you can simulate AND or not, using the operations you suggested, then that's as powerful as the model that we're going to do.
How would you evaluate this?
Right. So we'll talk about that in a little bit, but that's an excellent question that's coming up.
Thank you.
Yeah.
I was running the code that you had put up, once on Ed, I think, for
Mhm.
the encoding thing.
Right.
And when I wanted to decode a list of lists, it would only give me a list of empty lists.
Oh, really? Okay. I'll check that then.
Yeah.
Maybe there's a bug in there. Should not have been there, but I'll check. Yeah, thanks for it. Okay. So before talking about Boolean circuits, I want to do something else just for ease of for visual aid, really. Is there are these diagrams that people draw when they talk about, an AND gate is often denoted as something like this. The way to interpret this is I have two input wires, which are going into my gate device. Think of it as some electronic box, which then outputs the AND of the 2 bits. Okay, so this is the output wire. Right. So imagine you have many of these Lego pieces. You can feed different input wires and then you get an output wire. And then you can combine these things by passing this output wire maybe as input to another gate or another unit of this form. Okay. So this is a notation for and OR is or not is denoted something like this. Right, this is A, outcomes not of A. So the input wire takes A, the output wire gives a not of A. And then finally, you also have the OR, which is like an arrowhead. There's a point here. And an OR are annoyingly very close to each other. So these are not notations that we came up with. There's been around for almost a century now. People in ED especially build things using this. Okay. The input wires feeding into output wires. So now I can draw a circuit diagram for the things that we already saw. So for instance, for XOR 2, I can write down a circuit diagram that does it. Right. So I have an input, which is A. I have an input, which is B. And these are going into my gate operations. Right. So what was our formula for it? It was AND A, comma not B, or let me write it down a little further down, which was A and not B, or not A and B. Right. So, I can write down a circuit for it. So it goes into, let's say, not gate, and then this goes into an AND gate, right? And then the symmetric thing. Okay, and then I just have to feed both of these through an OR. Okay. So these are the not operations, and operations, and OR. So this is a circuit diagram for XOR 2. And if you're really interested, you can try and draw something for XOR 3 and majority, but it would get messy pretty quickly. All right. And there's this whole VLSI logic and programs for drawing out these things and laying out various circuits on an actual physical board if you want to. Right? Okay. So how do I define Boolean circuits? You can see here that the main power is in chaining these things. I can feed the output of one gate as input, as one of the inputs to another gate, and then do all kinds of things on top of that. And here, I'm also kind of passing the input to two gates. That's also fine. Why not? Okay. So to formalize this, we need some concepts from graph theory. In particular, we need the notion of a directed acyclic graph or a DAG. Okay. You might have seen this in CS 180 or in 32. So a DAG is essentially a graph where a graph, you have a set of vertices and a set of edges, which are unordered pairs, which, since we're talking about directed graphs, it's going to be ordered pairs, right? You have a set of vertices and an edge is a pair of vertices, which tells you, okay, there's an edge from 1 to 2, from 3 to 4, or something like that. So a directed graph is acyclic, meaning there are no cycles in it, if it has no directed cycles. Okay, so let me just draw a picture to make it clear. Right, so let's say these are my vertices, and then I can start drawing edges between them. And maybe this is one edge. Maybe this is another edge. This is one more. Okay, so this is the directed graph. So an edge with an arrow pointing in is an incoming edge, and an edge with an arrow pointing out is an outgoing edge of this vertex. All right. And you can see that, from the picture, it looks like this does have cycles in it, but these are not directed cycles. I can't follow the edges in the direction that are of the arrow to form a cycle. Can't follow those edges to get back to where I started. At least I think that's the case, yeah. But let's say, I add one edge here. Maybe, let's say this guy. Suppose I add the blue edge. Would it be a DAG still? No, right? Because I can just do this. Okay. So now I can follow the edges in the direction of the arrows and not a DAG with this edge, right? Because I can follow something like this. Oops. Yeah, maybe this is simpler. There you go. Okay. So I can follow these three edges in the direction that they're pointing and go back to where I came from, which is not allowed in a DAG. Okay. This is an important concept. So if it's not clear, please let me know, because we're going to use this again and again over the next several lectures. All right. So now we are ready to define Boolean circuits. It's a kind of a mouthful, but the intuition is that we'll associate circuit with a directed acyclic graph, right? So Boolean circuits as a computational model are just going to be DAGs, okay? For intuition, if you go back to this diagram, right? So let's say, maybe I'm going to think of each of these gates as a vertex. Okay, so you can kind of see a DAG here already, right? Because there are arrows on these things which take you from one point to the other. And you have the vertices, right? So imagine we are now going to generalize this to arbitrary graph. I have a directed acyclic graph. I'm going to associate vertices with gates or basic operations. And the edges will correspond to the wires that will carry out the answers. Okay. So an NMS. So I'm giving you 3 parameters. N is the number of inputs. M is the number of outputs. And S is the size of the circuit. Okay. So for XOR 2, it had 2 inputs, 1 output. And depending on how efficient we are, we'll get a circuit size. Right? So if you go back here, that would be 2, 1, and how many gates do we have? 1, 2, 3, 4, 5. Okay. So a Boolean circuit is, let me actually write it slightly differently. A NMS Boolean circuit. Again, this is the number of inputs, number of outputs, and the size is a DAG, directed acyclic graph, with n plus s many vertices. Okay, so all the information about the circuit is going to be contained in this DAG. It has n plus s vertices, and the graph should satisfy some properties. It's not any arbitrary graph, but it should satisfy some properties. So what are these properties? Exactly n of these vertices are labeled as inputs. Okay, so as inputs, which will denote as x0, let's say x1, x2, all the way up to xn minus 1. Okay, so there are n inputs. Each one I'm going to denote x0, x1, and so on. So there are n nodes in my graph where each one corresponds to a specific input bit, right? And then there are the other that takes care of the n vertices. They correspond to inputs, but then there are s vertices, right? The other s vertices are gates / basic and or / not. Okay. So each gate is labeled as an AND or an OR or a NOT. So I have to tell you what label is associated with each gate. So if I go back to this DAG and maybe just change an AND to an OR, change the label, is going to change the entire thing that's being computed, right? Yeah. Yes, they will be. Yes. Not necessarily. I mean, we can reuse some of the variables. Let me finish this. That should answer your question. We could do that, but we can also do this. There are many options of defining it, equivalent ways, really. Okay. Right. And so each gate is going to correspond to each node. Each of these other S things is going to correspond to a gate. But there are some constraints, right? If I want a vertex to correspond let's see what happened here. Oh. All right, we have to wait 30 seconds. So if I want a gate to correspond to an AND operation, how many incoming edges can it have? It should have exactly 2, right? And how many outgoing edges can it have? Well, why only 1? Maybe I want to give this output to multiple other times, multiple other gates. I want to use this output multiple times. Why not, right? But the main thing is that the input wire should only be 2. In some sense, I can duplicate the outgoing bit. Okay. So each AND gate has 2 in edges. Okay, so 2 edges which go in with an inward arrow. Each OR gate has 2 in edges. And finally, each NOT has 1 in edge. Okay. So this specifies the computation, it specifies what we are doing. And finally, we have to tell, the question of outputs, right? So let's say that exactly M of the vertices are also labeled as outputs. So the outputs are y0, y1, all the way up to ym minus 1. Okay. So the wires coming out of these nodes, those would be the output. Any questions? Okay, so let me draw one, maybe one figure to make it clear. So the way to picture it is somewhere we have the nodes corresponding to, oops. Right, so these are my input vertices, x0, x1, up to xn minus 1. Okay, and then I have these wires. Right, and they go, for instance, maybe I have an AND gate here. Maybe I'll have a NOT gate here and an OR gate here. Okay, so on and so forth. Okay. And some of these things are also labeled as outputs. Maybe I say this is y0, this is y1 all the way, and there's something else. Maybe the output of another not is ym minus 1. Okay. If it helps, you can think of the inputs always being all the way to the left, and maybe the outputs to the right, but they don't have to be. It could be anywhere. You might use this output again. All these minor things don't matter too much. And they change the definitions a little bit, but not in a substantial way. We just had to pick one convention, and I'm just picking this convention because it's kind of easy enough, and it's also the one that's followed in the book. All right. But this is it. This is our very general model of computation. Yeah, there's a question? Not necessarily. They could also be the input sometimes. Right? Sometimes, maybe you'll say, okay, I just want to pass this input along as the output. It could also happen. It's a good question. Yeah. What is the size? Well, basically that means you're not doing the circuit itself. You want it to satisfy these properties. So by definition, M would be at most S. But if you wanted more outputs, then you just put more gates in it, right? Or you just change the nomenclature or something. Okay. Like, you might have to duplicate some things. That could happen. Any other questions? All right. So that's what a DAG is. You start with a DAG. Sorry, a Boolean circuit is. You start with a DAG and you associate some computational meaning to this DAG. When you write down the definition, okay, it's a lot of words on a page, but the intuition is simple, right? The wires denote, kind of information flow, and the gates denote how you're processing that information. Okay. But remember this vision that we have of wires passing and so on, that's happening in our head. Formally, all we have is a graph with some directed edges, right? Okay. So this is all well and good, but how can I now connect this model to what it means to solve the problem? As I recall, our goal was, we have a function that was specified to us, and we want to compute it. We want to get an implementation for it. And our goal is to get an implementation in terms of Boolean circuits, right? And we define Boolean circuits as this DAGs. Good, but there's some mismatch, right? So DAGs, as I defined it, I haven't told you what is input and how do you actually compute the output. Right? It's kind of clear when you look at it. You'll say, okay, I give the input, and then I look at the function that you get by kind of processing the information, right? Or at least that's what you want it to do. Okay. So let's talk about that. Defining what a circuit computes. Okay. So how can I say, okay, the circuit is doing something, there's input nodes, this is output nodes, but what is the input output behavior? Any guesses? Somewhere, it should be important that I have a DAG and not a cycle. Why is that important? Because, if I'm writing a program, the input cannot be the output of the program. That's too recursive, at least for the time being, right? So we want some order of things, and that's where the fact that there is no directed cycle is important. So there's this notion of left to right in the diagrams that we're drawing. There are inputs which are going into the gates, and then they're going into the output. right? If I alert cycles, then I can maybe put this output wire as input here, and then I'm completely lost. What does it even mean, right? So to avoid those things, we only looked at DAGs. But how do I get around and define the input-output behavior as specified by Boolean circuit? Any suggestions? We need one more concept. Like, any DAG has something which allows us to get an order in which to do the processing. Yeah. Exactly. Right. So if we want to process the information, right, somehow the gates, the computation should have to go in order. If I go back here to figure out what this OR is doing, I need to first know what this AND did. And for this AND, I need to know what this NOT did, right? But if I want to define it this way, what prevents my graph from saying, okay, this NOT also needs this OR? At that point, I'm completely lost. It becomes a bogus model, right? But the nice property of DAGs, directed acyclic graphs, is that that cannot happen. And this comes from what is known as topological sorting of DAGs. Okay. So what does topological sorting mean? It means that if I have a DAG, then there is a natural ordering. I could place the vertices from left to right so that all the edges only go from left to right. Okay? I don't have any back edges. Any DAG, you can do this, right? G is a DAG. Then there is a layering. I'll call it H, which is a function from the vertices to natural numbers such that for every edge I comma j, h of I is less than h of j. Okay, so you're basically, you should imagine I'm placing the vertices in layers from left to right so that every edge only goes from a layer which is occurring further to the left to a layer to the right. And this number h tells you which layer a vertex is in. Okay. So let's do an example of this. Right, maybe, okay. Right, so let's say my edges are I think it's a DAG. Yeah, it's a DAG. All right, so let me just number them however which way. Okay, so these are, I have 5 vertices, these are the edges, and there is no director cycle in this graph. Right? And my claim is you can layer any DAG. You can find a layering so that the edges will always go only from left to right. Clearly, in this particular diagram, it is not true. Right? But how can I do that? Any suggestions? Let's say I want to somehow redraw this graph so that visually that property is true. Well, I'll start by giving a hint, which is C okay. C is here. Okay. I'm going to say that C is the leftmost vertex. Yeah. All right, that should work. Perfect. Let's try that. C and D, A and B, and E, right? So D, A, B, E. Perfect. So let's draw the edges again. The edges are from C to A and B. Okay, maybe let me use a different color. And D to E and B, right? And then, well, actually this doesn't quite work because A to B is an edge. So let me shorten it a little. A, and now we're good. Okay. And then you also have B to E, right? So you can imagine that, does this make sense? So we redrew the edges now so that all the edges are only going from left to right. So that's a topological sorting. And I can say define my layering so that, let's do that. Okay, so these are fun things which have h equals 0. This is the first layer. I'm going to say h of C equals h of D equals 0, right? And then the next layer is this guy. H of A equals 1. This is the third layer. H of B equals 2. Finally, we have H of E equals 3. Okay, so this is a layering of the DAG so that all the edges respect the ordering given by the layer. Right? And for any DAG, there may be multiple layerings, right? I didn't have to put C and D in the same layer here. I could skew them whichever way I want. It wouldn't change the property, right? That's fine. I don't care. As long as the edges are not kind of going back or in the same level, I'm fine. All right. So this allows us to take the leap from a definition of DAGs to actual computation. Meaning, we can now go from circuits to computation via topological sorting. Okay. So if I give you given a Boolean circuit with n inputs, m outputs, s gates, I can define the corresponding computation or quote unquote computation as follows. Okay. You first layer the DAG via topological sort so that all input vertices are in layer 0. Okay. So push all the inputs to the left. They are in layer 0. And then once we have computed, by computer, you should imagine the wires actually carry the values that we want. Like really imagine, there's electricity flowing. 0 means there's no electricity. 1 is there is electricity, or like, whatever fluid or something like that. So we have computed in layers 0, 1 through L minus 1. Okay. So once we have the order, we can kind of take the computation layer by layer, right? Because we know that to compute what's happening in layer L, I only need to know what's in the past. All the edges are only from left to right. So all the incoming edges would already have their values done. So now for a vertex in layer L, if an AND gate assign it the value of AND of its incoming wires, right? It's an AND gate. I'm just doing the, what's the most natural thing. I'm saying its value is the AND of the incoming wire. And this is consistent because the incoming wires have values which are already defined. Then if an OR gate assign it the value of OR of incoming wires. It's and then if it's not, same thing. Assign not of incoming wire. Okay. And what should the output of the circuit be? So the output of the circuit is going to be a binary string, which is m bits long. And the jth bit of the output is exactly the value assigned to vertex labeled yj. Okay. Does it make sense? So you go to your circuit, you look at where the output gates are, you look at what values were assigned to it as you did all the value assignments, and then that's going to define what your output is. All right. So now this is a fully formal model. Given any DAG which satisfies these constraints, I had told you what's the expected output of this, right? And we can now correspondingly define a function, right? Any Boolean circuit, which is a DAG, which satisfies these properties, gives us a mapping from inputs, n-bit long inputs, to m bit long outputs. All right. Okay, so any circuit defines its own function. It transforms inputs to outputs when we follow these steps. Okay, any questions about this? All right, so now let me finally connect. So we have an implementation of things. We have a language to talk about how to make a sequence of steps, do some computation. And now let's connect it back to what we wanted to do in the first place, which was to solve problems, right? So we say a circuit C computes a function f, right? So remember, a function, you should think of it as a specification, and a circuit as an implementation that you came up with for solving the problem, right? So if f of x equals c of x for all inputs, okay? So the circuit computes a function if on every input you match the behavior that you want. Okay. Any questions? So let's do one dummy run. Okay, so we said, okay, for XOR 2, this was our circuit for XOR 2, right? So let's see what happens when I gave it the input 1 and 0. Luckily for us, this is already topologically sorted in that the wires are only going left to right. So we don't have to do much things. So for NOT, the output would be, what would be the output on these wires? 1 here and 0 here, because 1 is coming in, it's getting flipped, right? And here you're getting 1 and 1. So what should the output be? So on this wire, the value assigned to this AND is going to be 1. The value assigned to this AND is going to be 0, right? And then we have 1 and 0. So this is going to be 1. And I didn't specify it before, but I have to say that this is the Y0. This is the output node as well. Okay. So clearly C of 1 comma 0, we computed assigning the nodes value, and we look at what's the value assigned to the output. It's 1. Okay. And you can do the same thing again. If I say C of 1 comma 1, you start following this thing, start assigning values. Whatever is the value assigned to the output, that's the final output. Okay. And now we have a concrete model of computation. I tell you, okay, my goal is to compute the AND of 2 n-bit strings. Can you write down a circuit for it? What would it require? You have to draw me a circuit, right? Tell me a DAG such that C of x equals f of x for all inputs. Okay. Any questions? All right. So all of this is very good, but there should be something really nagging you, right? Does the choice of the gates matter? Does the choice of gates matter? Why and or not? I mean, we have 3 basic steps here. What if I drop one of them? What if I drop or? Is it okay? If I drop and, what happens? If I tell you that in your circuit model, you don't have any OR gates, right? Imagine you have this Lego pieces, right? You have 3 bags full of and, one full of or, one full of not. One bag is missing. Can you still do the computation that you wanted to at the beginning? If not is missing, that's a huge problem. Then you cannot do even simple things like XOR of 2 bits. But if one of and or is missing, that's fine. It turns out that you only need one of and or and not if you really want. Okay, but how can we even talk about such things? Right? So why these and not something else? Okay, and it turns out that the choice of these basic steps really doesn't matter too much. As an example, we are going to talk a lot about one more gate, which in some sense can be used to subsume and or not. Like we have 3 different gates. Some of the specification became a little complicated, right? You needed a DAG, and then you needed to label each gate with, okay, it's an AND operation or an OR operation or a NOT operation and so on, right? But we can avoid all of these with another simple operation called NAND. It's in a sense like, one ring to one operation to rule them all. Okay, so what is NAND? It takes 2 bits, just as before, outputs a single bit, and what does it do? Well, it's really just in the name. NAND is short for not of and. It's a very literal thing, just not of and of A comma B. Okay. Just as we defined Boolean circuits, I can also define this whole new world of NAND circuits. Everything is exactly the same as Boolean circuits, but only allowed to use NAND gates. Okay, so you cannot have any AND or NOT gate. You have the same situation, like you'll say, okay, I have a DAG, I have some number of inputs, I have some number of output things, but every gate is now only a NAND gate. Okay, I mean, just for clarity, we'll go over every step of the definition again, just for NAND also in the next class. Okay, but once we have this guy, we can also talk about a different computational model or seemingly different computational model, which is NAND circuits. Okay, maybe there are some things that I can do with NAND circuits, but not with Boolean circuits, right? In the break, someone was asking, it seems more natural for me, since we're talking about strings, to talk about operations which allow me to cut off strings or do shift operations and things like that, right? And if you're familiar with C programming or something, shift operation is something very basic again, right? What happens if I start with those as my basic operation? Would I get a new, different, more powerful computational model or something weaker, right? So in the next class, we'll address that, whether changing these basic operations can actually change the full power of the model. What functions can you or cannot compute with just Boolean circuits? Can I multiply n-bit numbers using Boolean circuits? How about NAND circuit? Okay, we'll talk about that on Wednesday. All right, and remember, today's first homework will be released. I'll see you all on Wednesday.